Okay, so last times we have discussed the LED. Uh, what I have seen in LED, we have seen the LED is a DA structure. Am I audible now? I'm
Yes, sir.
audible. Hmm. So we have discussed these LED structures, LED geometries. I mean, different structures, DA structures. You have seen it. Mm. And also different parameters like internal quantum efficiency. And and we have seen this how internal quantum efficiency is affected by different parameters like surface recombination velocity, uh, yeah, self absorption, etc. Those things are there. And with this, once you get this internal quantum efficiency, we can estimate the power emitted by the LED. The most important, how much power is LED power, how much power an LED can emit. That is most important, considering those factors. Right. And also in this context, we have seen when the LED is modulated with some signals, then modulation rate is limited by the diffusion capacitance. That is due to the stored charges. Right. And we have seen it. This modulation bandwidth can be determined if you know the effective carrier lifetimes. That is, modulation bandwidth, it is inversely proportional to the effective lifetimes. Those things are, we have seen it. Anyway, so these things are there. Now we'll see the lizard diodes. Sources I told you initially can be that can be used for fabric systems, either coherent sources and coherent sources. We have discussed several times, and all natural sources are incoherent sources. LED also LED is an incoherent source, right? But this type of incoherent sources cannot be used for single mode fiber. In single mode fiber, you need coherent sources like laser sources, because single mode fiber dimension is very thin. So if you use the conventional sources, then very less light will be coupled, because in that case light is not directional. Right, light energy, it is divergent in nature. Right, so very less light will be coupled, almost nil light will be coupled within the fiber. That's why we need some sources that will have highly directional property, right? Like the laser sources. So we'll focus on laser sources, particularly on laser diode. Other lasers are, in fact, if you see the lasers, it can be gas lasers, it can be liquid lasers, solid lasers, it can be semiconductor lasers. Right, gas lasers like say helium neon gas, helium neon, argon ion is a red lasers, argon ion is a green lasers, blue greens you can have it. Liquid lasers are there. I mean, dye lasers, Rhoramine 6G, different dye lasers are there. Here you can have arbitrary wavelengths. Solid lasers, like say ND, these are generally dye lasers. Organic dye is used, dye lasers. And solid lasers, like say ND glass, very high power lasers, ND YAG, neodymium YAG, ruby lasers, etc. These are the different types of lasers. Also, we can have the lasers based on semiconducting materials, and those are called actually laser diode (LD), based on pin junctions. So these are called laser diode. And the question is why so many types of lasers? Why you consider these semiconductor lasers? The answer is very simple. If you use these other lasers, you need external modulator to modulate their optical output. Ultimately, in the fibers, within the fiber, you see light is not the simple continuous light. It's a modulated optical light, modulated optical beams that is propagating, modulated by the modulating signals, right? So that is actually propagating. So you need modulations. So if you use this type of sources other than semiconductors, you need external modulator. External modulator is required, right? External device is required. But if you use semiconductor sources, simply, I mean, if you semiconductors, then if you change the drive current, you can modulate their optical output. So don't require any external modulator, right? That can this LED or laser diode can be placed in the collector circuit of transistor, BJT, FET, etc. And accordingly, you can modulate their optical output. So the driver circuit is also there, of course. That is probably you have done it in the laboratories. You need driver circuit for that to change the current according to the modulating signals. Okay, so that is the reason we are considering the semiconductor lasers or laser diode. Now come to the LED and laser diode. LED and laser diode, if we just compare, we have seen these output. It's a threshold device and it's a the almost linear device. I mean, if you give this current, you'll get the output. We have seen it. This is almost increasing the current, power will increase. But in case of laser diode, it is threshold device. Initially, there will be no light, but after a certain threshold current, there will be a dramatic increase in the output. That is the reason not only for laser diode, for any other laser sources also, right? For other sources, there is no need of current, but there is some pumping power is required. Initial, that is called threshold power. And here it is called threshold. At this point, it is the threshold current. We'll see it, what is the threshold condition and the corresponding current also. We'll see it. So this is the difference between these LED and laser diode. Of course, their structure is almost similar microscopically. Here also you can have DH structures. 3-pi compound semiconductors will be there. NPP, LNPP, or NNP, like these things. 2 junctions will be there. But apart from that, in laser diode, if you microscopically examine, something different is there. Means here light is generated within a resonator. You need a resonator. That means we need a feedback. In fact, in this case, optical feedback is there. Right? Because of this feedback, it converts the device into an oscillator. And depending upon your design, only certain frequencies you can have it within this laser diode. So laser diode, though it is, laser means light amplification by stimulated emission of radiation. So it is not an amplifier. Basically, it is an oscillator because of the feedback. So we'll see in the geometry how feedback is realized. Feedback can be obtained in laser devices. Before that, we should know the lasing principle, right? Operation of laser, if you just see for all laser sources, this is common. Lasing principle is common to all laser sources, whether it is gas lasers, whether it is liquid lasers or dye lasers, or can be solid lasers or can be semiconductor lasers. Here, this lasing principle, it is based on 3 mechanisms. One is photon absorptions. Second one is a spontaneous emission. Third one is the stimulated emissions. Now, to understand these things, you consider a 2-level diagrams. Say these 2 levels, E2 and E1. And let us say the population densities of this, it is an enclosed system, only 2 levels are there. And population density is N1 and population density is N2 at the higher levels. But initially, there will be no carriers, there will be no active centers, you can say, in the upper energy levels, because every particles or every object will try to remain in the lower potential energy. So in the normal conditions, it will be highly populated E1s. It will be population will be in these lower energy levels. Now, when the photons strike on these systems, then photons will be absorbed. Now, obviously, the electrons will be excited and they'll go to the upper energy state, right? And that is actually when the H nu, I mean, when the photons strike on the systems, say H nu, then you see H nu, that is actually E2 minus E1, this E2 minus E1. Then because of these things, absorption of photons, as per the Planck's transitions, the electron will be excited in the upper energy state. But since there is only one state is there, the transitions between will occur between the 2 states, right? I mean, this is as per Planck's law. Whenever the photons whenever there is a transitions between the two states, then it can be either absorption or emission of photon. What is that? That is h nu equal to E2 minus E1. In case of absorption, that is h nu 1 to 2 absorptions, that is E2 minus E1. And in case of emission of, that is this one, lower to upper, lower level to upper levels. And whenever there is a transition from upper level to lower levels, then energy will be released. That is h nu. That is actually E2 minus E1. That is as per Planck's law, right? Now think about these things. Suppose when the photons absorb, then electrons will be excited. It will go to the upper energy state, but the upper energy state always it is an unstable state, right? Because every particles they will try to remain in the lower potential energy. So there will be after certain times during the lifetimes, it will come to the ground state. But whenever there is a transition from upper state to the lower state, just now I mentioned, there will be release of energy, right? And that is actually h nu E2 minus E1. So that means some emission will occur. That emission is called the spontaneous emissions, right? This spontaneous emission, this is spontaneous in the sense that you see, with this emission occurs from higher state to lower state without any external stimulations. Without any external stimulations, natural transmission. I mean, think about a mango tree. When you see, if you give some thrust, then mangoes will come to the ground state in the ground levels. Otherwise, when a particular time will occur, particular mango, ripe mango, then that will come to the ground levels, right? So there will be natural transitions whenever the excited electrons come to the ground state without any external stimulations. That is the spontaneous emission. But whenever the spontaneous emission occurs, okay. So whenever there is a transitions from these ones, so photons will be emitted, but these photons are random because all the mango tree, you see, will not the same instant they will not come to the ground levels, right? It is as per their time, right? So it will come to the ground levels. So that is the natural transitions, and in fact, in that emission, it's called the spontaneous emission. But there can be whenever photon absorption occurs, that can be another type of emissions. Suppose for a certain instant, electrons are excited and they are in the upper energy state. In that situation, if the photons strike on the systems, then you see the excited electrons will be forced to make a downward transitions, right? This time transition will occur by the external stimulations. If it occurs like these things, that times it is called stimulated emission. And the difference is that this time the photons emitted, they are in phase, but our phase difference remains constant for all of them, right? So that is actually the stimulated emission. When this stimulated emission dominates in a particular systems source, then emission means source will be there. So whenever stimulated emission dominates, that times you get the ledging actions. But don't think that conventional sources they are not having this stimulation. In fact, any source, there is a spontaneous emission, there is a stimulated emission. Probability is not zero, but the conventional sources, the probability of stimulated emission is very, very less, almost zero or very near to zero. But it is not zero actually. Some emission always would be there, stimulated emissions, but mostly dominated by the spontaneous emission. So if you can make something where stimulated emission dominates, that times you will get the ledging action or the ledging output. So how we can have the more stimulated emissions? That is possible through another technique, that is population inversions. What is this population inversion? just I mentioned N1 and N2, they are the population densities of the two levels. Initially, N1 is greater than N2, but if you make some means that so that the N2 is greater than N1's, then that is called the population inversion. So if this population inversion is maintained, then you'll get the leaching output. Now the question is, how can realize this population inversion in practice? So there are different techniques are there. Like you can see it here by injection of current in case of semiconductor lasers or laser diode, by injection of current. In case of solid lasers, by optical pumping. Solid lasers like say ND YAG, ND class, etc. by optical pumping, or by dye lasers, etc. by chemical reactions, or can be electric discharge, like say helium neon gas lasers, helium argon ion, in that case gas. There are different techniques are there for these to get the population inversions. So once you get the population inversion, next time the stimulated emission will dominate, and in turn you will get the leaching output. So this is the principle of leaching. This is the principle of leaching output, laser, right? I mean the leaching principle. It is based on three things: photon absorption, spontaneous emission, and stimulated emissions. Okay, we can estimate this. How much? How we can estimate the stimulated emission or the induced? Stimulated emission means induced emission or induced transitions, right? How can estimate the induced transition rate? Anyway, if you have any question in this leaching principle, you can ask. किसी कोई क्वेश्चन है तो पूछो.
Sir, how is population inversion done, sir? Like,
population inversion, say for normal conditions, for any system, suppose you take a pen in your hand, and if you release your hand, the pen will come to the ground levels or not. That means every particle will come to the ground state. That is the minimum potential energy. So initially, if you see for any systems, you see lowest energy state, it will be highly populated. It is population is always greater than the upper energy. Upper energy is almost empty. Ideally, it will be empty, but some active centers, some electrons may be there, right? But it is always N1 greater than N2, normal cases, natural cases. But if you make some means so that the N2 is greater than N1, that times it is called the population inversion. That means the density, carrier density, or the electron density, or the active center density, you can see. Since electron transition we are considering, so if the carrier density it is greater than the carrier density of upper energy state is greater than the carrier density in the lower energy state, that is actually ground state, then that situation is called the population inversion. In fact, in laser also, you see, if you go in deeper thought, actually the lasers, there can be 3-level lasers. Just now I'm showing it 2 levels, but it can be 3-level also. Suppose you can have like these things. This is a ground state, this is the pump band, and this is a upper energy state. This is a band, right? You see it here. Initially, all the atoms will be in the ground state, but whenever you give some technique like say optical pumping, is it is to get the population inversion. I mean, if you apply the current or optical pumping or some electric discharge, then what will happen? The ground state atoms will be excited. I mean, electrons will be in the upper energy state, right? This upper energy state, but this is upper energy, this pumping band, right? This band, you see, very soft decay, there will be collected in the upper energy state. That is actually called upper laser levels. Next, there will be transitions. When there were transitions, you will get emission of water. This is non-radiative, but it's radiative. So at a certain instant, you see initially this level is almost empty, but because of optical pumpings, you see the electrons will be collected in the upper energy state. So that this, if it is N2, this is N0 or N1, then N2 will be greater than N1. In that situation, it is called the population inversion. Normally, normal cases also all this is there, but you see, to get the population inversion, if you go into details, you need some metastable states. I mean, agar lifetime both short hai, so quickly it will with the transitions, but it is lifetime should be greater. See, all the metals cannot produce lasers. The laser, the metal that can produce lasers, that will have longer lifetimes. That is called metastable states. States having longer lifetimes. Just as the longer lifetime, so more centers will be collected, more carriers will be collected. So more carrier means it will be greater than the ground state levels. So that situation is called the population inversion. This is 3 levels. This is 2 levels. It can be 4 level also, like these things. Palm band. Next, palm band short decay. There will be apart. Not only the transition occurs from upper to ground. It can be. This is called upper ledger levels. This is a lower ledger level. This is the ground levels. So here also you can have the transition. There is the 4 level ledgers. Say 0, 1, 2, 3. समझ में आया क्या प्रोपोर्शन इन्वर्सन है?
Yes, sir.
हाँ?
Yes, sir.
Okay. अब देखो, now just because of this population inversion, we are getting the stimulated transitions or induced transitions. Let us have an estimate. How can estimate this induced transition rate? So if you see the 2-level systems, say this is N1 and N2, the density, population density, N1 and N2 of level E1 and level E2. Now, naturally, I told you, normally N1 is greater than N2, and this, in case of semiconductor, it is given by this, the Boltzmann relations. It follows the Boltzmann relations for this, the N1 and N2. So it is N1 upon N2, it is e to the power E2 minus E1 by KT. This is a Boltzmann relations. In semiconductor physics, probably you have read it, right? Population densities of the 2 levels. Now, also as per the Planck's radiation law, radiation, how can you express this radiation? The energy density in a particular frequency, rho nu, that is actually Planck's relation, it is 8 pi h nu cube by c cube into 1 by e to the power h nu by kt minus 1. As per Planck's radiation law, the photons will be treated. The radiation can be considered as a on the stream of photons of energy h nu, right? So this is the Planck's relations, right? So these two things, radiation can be, because I told you, photons absorption will be there. Next, there will be transitions. There can be upward transitions, can be downward transitions. So if you consider the probability of upward transitions, that is actually upward transition means absorptions, then what will happen at that times? If an atom absorbs a photon of energy E2 minus E1 energy of h nu, then it will be in the upper energy state. So the probability that an atom will absorb a photon of energy h nu will be proportional to the intensity present, this radiation density present, probability of upward transitions. It will be proportional to this, the intensity of radiation present or radiation density present, rho nu, and also depends on the time how many electrons will be excited in the upper energy states. That probably depends on the time also. So probability of upward transitions, it is proportional to rho nu as well as into delta t time intervals. So, and if you write in the equation forms, that will be constant of proportionality, you add it, that is B12 rho nu into delta t. What is B12? Because the transition is occur from 1 to 2, the constant of proportionality. Similarly, probability for downward transitions, when the photons strike on the systems, there will be a downward transitions. Electrons will be forced to make a downward transitions. That is P2. That P2, it is actually called, actually it is also, it depends upon this, the intensity present, photons, number of photons present on the systems. So it depends on the rho nu, also time interval delta t. But this time it is 2 to 1. That's why the constant of proportionality, it is 2 to 1, B2 1's rho nu. But apart from these upward transitions and downward transitions, also you can have, there will be natural transitions that I told you, because of spontaneous transitions. spontaneously emitted photons, right? So whenever there is a transition from upper state to the lower state, there can be forced transitions. Also, there can be spontaneous transitions. So in that spontaneous transitions, it does not depend upon the intensity present, it's a rho nu. So it is simply it depends on time intervals. So P3, that is the probability of downward transitions, spontaneous downward transitions, that is actually A21 delta T, right? So and why 81 means it is 2 to 1, and it is the constant of proportionality for spontaneous transitions. Actually, if you see this B12, B21, A21, these are actually Einstein's coefficients. It's Einstein's relations, Einstein's coefficients, and they actually determine the interaction of radiations with the um, electromagnetic field with matter. Right? There's some radiation with matter, right? The materials. And 81 is generally if tau space p the spontaneous transition, spontaneous lifetimes, tau sp, you see tau sp spontaneous, that the tau if lifetimes we have seen it is spontaneous lifetimes, then 81 it is 1 upon tau sp. So if you use these three probabilities, and if you consider the dynamic equilibrium conditions, then rate of excitations will be equal to rate of de-excitations. So rate of excitation means you see this is the rate of excitations 1 to 2 excitation rho 1 to P to 1 to rho nu into N1 into delta T. The N1 which is multiplied is the probability. When it is probability multiplied by the population density, you will get the rate of decay. Right. This is rate of excitations. And rate of decay will be see the probability of spontaneous multiplied by N2. It is because it is 2 to 1. Here also, this is the probability for downward transitions. This is the probability of spontaneous transition, and this is the probability of these stimulated transitions into delta T. Just now I mentioned, whenever there is a transitions from upper energy state to lower energy states, there can be spontaneous transitions or there can be stimulated transitions, right? So this is the rate of excitation equal to rate of de-excitations. Now, if you simplify it, you'll get rho nu equal to this. And also, we know the Planck's relations, rho nu, Planck's relations, what does it, this ones, that is 8 pi h nu cube, just now I've seen it, by c cube into 1 by e to the power h nu by kt minus 1s, right? H nu actually it is E2 minus E1, h nu. Right? So these two are identicals. So that means if you just consider these two, then you see it, what will get it? So rho nu from these equations, rho nu actually it is into this one, and if you just divide by into B1, B21 into B21 into, if you just divide it whole things B21 into in the numerator denominator, then it will be A21 by B21 and B12 minus minus, you take the minus, so minus minus plus it will be there, so it will be B12 by B21 N1 by N2 in minus 1, and N1 by N2 we know it is e to the power E2 minus E1 by KT, and from the Boltzmann relations. So that is E2 minus E1, that is actually h nu. So we are getting this these ones. So ultimately, you see what you're getting it, A21 by B21 divided by B12 by B21 into this one into minus 1. And if these two are identical with the same things, that means this must be equal to these ones. You see it 1 by it is the same things here. If you put it here, N1 upon N2 to the power h nu by e to the power h nu by kt, right? Then you see with the negative signs, 1 minus, or yes, it is just a minute. if we just put it these ones here. Here actually you see it here. Relations e to the power h nu by kt minus 1s, right? So it is here also e to the power h nu by kt minus 1. The same relation is here. So that means this must be equal to this one, and B12 must be equal to B21. If you just compare these the Planck's relations, this one, right? That means B12 equal to B21 equal to B, and this ratio will be A21 by B equal to 8 by H nu by CQ, right? So induced transition rate, actually it is W1, that is rho nu into B21s, right? Or since B21 equal to B12, so both are equals. And if you substitute the value of B21s or B, then you will get these ones. What is B? We just now have seen it. You see it here. A21 by B21. Actually, B21 equal to B, both the same, writing B. So B21, A21 equal to B into these ones. That means B equal to A21 CQ by 8 by H nu Q. That's what it is here. You see, A21 CQ by 8 by H nu Q. So in this way, you can estimate the induced transition rate. I'm showing you examples of, say, helium neon lasers here. Helium neon laser, how the lasing actually takes place in gas lasers. You can see these are the two levels, higher energy levels. These are whenever helium, actually helium neon lasers, neon is the active sensor. Helium is used to excite the neon atoms, right? So whenever pumping discharge takes place, they will go to the upper energy state, say F2, F1. Next, there will be collision with the neon atoms. So the neon atoms will be in the upper energy state, like say 1s, level 3s, 2s, 1s. They are the different upper energy states. Next, there will be a transitions from is there 2p, 3p, the energy states are there. So whenever there is a collision between helium and neons, then helium atoms will transfer energy to the neon atoms, and they will be excited in these states, 2s, 3s. And next, there will be upper energy states. There will be transitions from 3s, 3p, or 3s, 2p, or 2s, 2p, or 2p to 1s, or can be 1s to ground state. So not all are the transitions that will result the emission of photons. Generally, these 3s, 3p, 3s, 2p, and 2s, 2p, they provide the emission of radiations. But generally, helium neon is red. So generally, these two are actually blocked by proper designing and these systems 3.39 and 1.15. This is 1.15 most probably. 1.15 microns. So these two emissions are generally not required. So only red light is there in case of helium neon. So these are examples of helium neon lasers, right? Okay. If you have any questions regarding this induced transition rate, you can ask. Anybody? किसी कोई क्वेश्चन है तो पूछो.
Sir, this
कोई
is
क्वेश्चन है तो
part of Kaiser, sir. I didn't found this part in Kaiser.
everything will not get it in Kaiser, but these relations may be in given. Let me check it whether it is there or not. It is here. Final relations. Okay, hi. This is not probably this is not there. For any standard ledger books, you can have it. Just to show you what is the induced transition rate. For probabilities, probability is generally given. Let me check it. It is not there. No? Anyway, this is not there. So just to understand, try to understand these things. Anyway, if you have any questions, you can ask. It is not there. Yes, it is not there. बोलो कुछ क्वेश्चन है तो पूछो. Just to we are saying. Yes. बोलो.
नहीं सर, वो समझ में आ गया सर कॉन्सेप्ट इसका. नो क्वेश्चन.
वो एक्चुअली मैथमेटिकल ट्रीटमेंट फ्लो दिखा दिया तुम लोग को जो कैसे ट्रांजिशन हो रहा है. ट्रांजिशन तो बोल रहा है लेकिन एक्चुअली if you go into the little bit in details, then you can have all those things. Any ledger book, कोई भी ledger book में देखोगे इस तरह का मिल जाएगा. घटक का बेसिक जो घटक ledger books, कोई भी ledger किताब में ये सब रहता ही है. ledger डिजाइन करोगे तो इसमें ये सब का जरूरत. इंडस ट्रांजिशन को तो तुमको एस्टिमेट करना पड़ेगा ना, व्हाट इज इंडस ट्रांजिशन रेट. तो ये सब है एक्चुअली. थोड़ा ये था, वो थोड़ा सा एडवांस लेवल पर दिखा दिया तुम लोग. एनीवे कोई क्वेश्चन है तो पूछो, अगर नहीं है तो ठीक है. काइजर में नहीं है तो ठीक है. लेकिन कॉन्सेप्ट वाइज तो क्लियर होना चाहिए. कुछ क्वेश्चन है कि इसमें?
नो सर.
ओके, नेक्स्ट देखो, लेजर को हम लोग थ्रेशोल्ड डिवाइस बोल रहे हैं. वी हैव सीन इट आउटपुट, देयर इज नो आउटपुट. इनिशियली इफ यू गिव सम करंट there will be no output, but after sometimes you're getting the output. That means some threshold current or threshold power is needed, then only it will be, there will be a output. That means it's a threshold. All laser devices are threshold devices. That means some threshold condition is there. So what is this threshold conditions that you see it? This portion it is there. Threshold conditions is there. It's not in so much details, but anyway, I'll just give it. You can understand if you just go through it, what I'm saying. So quickly see why it is called a threshold device. Because you see, if you see any laser structure, whether it is semiconductor or any other lasers, generally you can think about there is two mirrors are there at the ends, and in between there is a lasing medium will be there. In case of semiconductor lasers, generally these mirrors are not there. Simply a slab of semiconductor is there, PN junction will be there, but at the end faces some coatings are provided so that it can behave as mirrors. So anyway, by or some proper cutting by clipped facet also, by proper cutting also, this can act as a mirror. That means some mirror activity must be there. So that's what I am representing. The two mirrors are there, laser devices. And in between there will be a lasing medium. This medium can be semiconductor, maybe gas, maybe solid, like these things. Right. Now what happens whenever you give some current or some pumping, the photons will be initially, there will be spontaneously emitted photons. You cannot avoid the spontaneous emitted photons. So these spontaneous emitted photons, they can move, they will be emitted in all directions. But some of the photons, they will move towards this mirror. Suppose the photons or the light energy that propagates along this mirror, that will be reflected by this mirror, and again through the reflections, again it will enter into the mediums and it will be reflected by these mirrors. Now you see in the laser geometry, one mirror must be of 100% reflection mirrors for any lasers, and other mirror must be of the other side. Can be 90 to 95% reflection. Only 5 to 10% light, 10% light is coming out. That is too dangerous, right? Laser light for all, even the laser torch, you have seen it. So in that case also, only 5 to 10% light is coming out from the device. So one mirror should be 100% mirrors. But when this light travels back and forth, that means feedback is there. You see, it is fed back into the lasing mediums. So whenever this such feedback mechanism is there, there will be gain and there will be loss. What is the gain? Gain is provided by this medium because photons are emitted. That means that is the gain. And what are the losses? Loss will be due to the mirrors, due to the mediums, and due to the mode conversions. You see, first loss is due to, if you consider the one complete round trip from any position to reflected by this mirror, again you enter the mediums, again reflected by this mirror, then you see there can be loss in the transmission or absorption in the mirror. Mirror to ideal mirror nahi hai. Agar 100% reflection बोल रहा है, लेकिन कुछ तो it is never possible to 100%. Some portion will be transmitted, some portion will be absorbed, right? For every mirrors. So that is the absorption and transmission loss. Now diffraction loss, say light can be considered as a spherical waves, and this mirror is of finite dimensions, right? It cannot be of infinite dimensions. So finite dimension means you see a portion of the wavefront is only reflected back, not the full wavefront. To reflect the full wavefront, this mirror should have finite dimensions. वो तो possible नहीं है. So a portion is transmitted, reflected back. That means there will be loss, diffraction loss. This is by both the mirrors. Also, when the photons traverse through the mediums, there will be absorption. Also, there will be scattering. So there will be absorption loss and scattering loss. Also, laser is a multimode, is a resonator. So multimode will be there, and many modes will be generated. And whenever conversion, mode conversion takes place from lower order mode to higher order modes are less tightly bound, so they will be generally they will not be sustained within the cavity, so loss will be there. So during mode conversion also loss will be there. So these are the different losses. So you are having gain, you are having loss. So one condition will reach when gain equal to loss, that is called the threshold conditions. And when you get the output, when the gain just exceeds the loss, that times you get the lasing output. Now the question is, that means gains should be always greater than loss? No, gains should not be always lesser, will not be always greater than loss. That is because you have seen this principle. It will be once it is highly populated, next it is depopulated. Again highly populated, again depopulated. So actually gain curve, if it is threshold, it is clamped at threshold. Means populated, depopulated, populated, depopulated. This will be there. So some spikes will be there microscopically if you just think it. But anyway, it's a threshold divides, because when gain is equal to loss, that is called the threshold condition. When the gain just exceeds the loss, that power difference will be treated as the lasing output. So this is the threshold conditions. And now we'll find out what is the gain parameter at threshold. I mean, let us have an estimate of these things, expressions, find out expressions of this gain in terms of the laser parameters. That we'll see. Next time we'll see it. I think this it is there in your yes, this expression is here. Final expression is here. I am just deriving it. G threshold. That will see it next times. Okay, then next time we'll see it. If you have any questions, पूछ सकते हो. किसी का कोई क्वेश्चन तो पूछ सकते हो. थ्रेशोल्ड कंडीशन में कुछ क्वेश्चन है तो पूछ सकते हो.
No, sir. Thank you.
Next time we'll see the gain expressions and other expressions, modal concept, how many modes are there, how you can determine how many modes are there in the lasers, what is how modulation rate is determined, affected by different lifetimes. That will see it. Other parameter also we'll see the laser diode structures. What are the different type of structures? It can be paper types, it can be distributed types. That we'll see it next time. Okay, today this much. If you don't have any questions, I'm just this one. No one except Harshvardhan, no one else put a question or put a sound. Really surprising. No one else. How you are getting the marks, that is really surprising. Anyway, let us see in this way. To consider it.